Welcome again to Physics 371 Online. Today, having discussed the origin of magnetic fields and summarizing that through the Biot-Savart law, we're going to look at the divergence and curl of the magnetic field and develop something called Amperes Law. So let's launch right into it. We'll consider first the special case of an infinitely long straight wire because it will enable us to get the results that we want fairly easily. And then we'll be able to see that these results can be generalized for more general cases of currents. So imagine this current in a long straight wire along the z direction, and we already know the magnetic field that is produced by this current. We know that it loops around the current in the phi direction, if we're looking at this in cylindrical coordinates, so that at a perpendicular distance s away from the wire, the B, which of course loops around the wire, is given by mu naught I over 2 pi times the distance in the phi hat direction. And in case you're wondering which direction the phi hat is, with your thumb of your right hand along the z direction, the fingers curl around the z direction in the sense of positive phi hat. So, by inspection, just looking at this kind of field, we can see that we should expect it to have zero divergence. The field's not spreading out in space away from or toward any single point. But of course, we also expect this field to have a non-zero curl because it curls around the wire. So let's work these things out for this special case. First, we'll start indirectly. Let's integrate the quantity B dot dl around an arbitrary loop that encloses the wire. All right, so in an end view now, looking at the current coming straight out of the page at us, let's imagine an arbitrary shaped loop. It doesn't have to be a circle, doesn't have to be anything, as long as it's a closed loop that surrounds the wire. And we'll be integrating in the counterclockwise direction, which according to the right-hand rule is consistent with having your thumb along the direction of the current. So the dl vector at this point here points in a direction indicated by the arrow, and right at that point the current, or the dl vector, is a distance s away from the origin. We're assuming that the z-axis is of course the current axis. So in order to integrate b dot dl, we first have to write down dl, and in cylindrical coordinates, you can check in your textbook that this is correct. dl is given in this form. It's ds s hat plus s d phi phi hat plus dz in the z hat direction. And remember that s, phi, and z are the cylindrical coordinates that we want to use. So easily, right away, we can get a very simple result that has great power because it's quite general. And here you'll see the integral of b dot dl. If we just examine the b vector, it only has a phi hat component. And so when we dot it into dl, which generally speaking has components along s, phi, and z, the only thing we get with the dot product is the product of the phi hat components. So we get mu naught I over 2 pi s from the b, and then we get s d phi from the dl. The s's cancel. And so and then when we pull out the mu naught I over 2 pi, all we're left with is the integral of d phi around a closed loop, and no matter what shape the closed loop is, we'll always just get 2 pi for that. And so it will always cancel out to give us mu naught I. This result, in other words, is going to be the same for any shape of loop as long as that loop surrounds the wire. And that's very important. So if we, additionally, we can generalize to the case of not only any shaped loop, but any number of currents, because for any current passing through that loop, we would just add it to the other currents, because this principle operates in superposition. The magnetic field that corresponds to those currents, if we have more than one current, we just add up the magnetic fields. So this result, if we imagine that we've got lots of currents passing through the loop and we add them up to get a total of I enclosed, then the result of this integral could be generalized. So this closed line integral of b dot dl is equal to mu naught times the current enclosed by the loop that we are using to do the integral. And this is a statement of Amperes Law in the integral form. And I won't prove it to you, but I will just argue that even though this result applies strictly only to a long straight wire, we can prove it to be true for any arbitrary shaped current. And you can look at the textbook for a more general proof. Now let's take this expression and put it in the differential form, which is a little bit tidier. Although the integral form is actually the one that we will use most often in applying Ampere's law to a real-life problem. But the differential form is important too. So first, if you look at the left-hand side of Ampere's law up above, you'll see that it's a closed line integral of a vector function dotted into dl, integrated around that closed loop. And Stokes' law says that for any arbitrary vector field B is equal to the surface integral of the curl of that vector over some surface. And so as a result, the left-hand side can be written equally well in terms of the curl of B. The right-hand side we can also write imagining that there's going to be some current density J spread out in space, and so the loop then will define a certain amount of that J that passes through it, and that's the total current. So the current enclosed by the loop, now on the right-hand side of Ampere's law, mu naught I enclosed, we can write as mu naught times the surface integral of J dot dA. And this again just comes from the definition of a volume current density J. So now we've expressed each side of Ampere's law in a slightly different way. So the left-hand side, we'll write that as the curl of B dot dA integrated over a surface. And the right-hand side we'll write as mu naught J dot dA integrated over a surface. So what we end up with is the equality of two surface integrals. And for these two integrals to be equal to each other, in general, the only way that can happen is if the integrands are the same. And so this implies that del cross B is equal to mu naught J. And it's very nice because it tells us that B, the source of magnetic fields, is currents expressed through the current density J, right? And that those currents, the strength of the current, is proportional to the curl of B. So this confirms our expectation that this kind of a current density, this kind of a straight line current, should have a non-zero curl around it. And this is Ampere's law expressed in differential form. It's nothing more than the integral form of Ampere's law with a little bit of geometry thrown in order to express it this way. And in class I've called these forms of Maxwell's equations the t-shirt forms because they're nice and tidy and not cluttered up with integral signs. Now, that gives us the curl. But what about the divergence of B? So let's go back to the long straight wire with current I. We know the magnetic field is mu naught I over 2 pi s phi hat. And so let's just straightforwardly take the divergence. So the divergence in cylindrical coordinates is given as follows, just right out of the textbook. And you can see that first of all there's no z component of B, and also there's no s component of B. So the first term and the third term give 0. The middle term, when we look at it, we've got the derivative of the phi hat component with respect to phi. Well, the phi hat component doesn't depend on phi. It only depends on s. And so the divergence of B is 0. And I mentioned before that that might be what we would expect, realizing that the magnetic field is in the form of loops that surround the wire. And so it doesn't diverge or converge to any point in space. And so, in other words, the divergence of B is also equal to 0. Once more, this was only derived for the case of a straight wire, but using the Biot-Savart law to write down B, we can show that the divergence of any B that arises from currents gives us a value of 0. Sometimes, because of the analogy to del dot E, which was the differential form of Gauss's law, sometimes this equation is called Gauss's law for magnetism. But other books just leave it without a name. In any case, it's the consequence of the fact that magnetic field lines always form closed loops, and that's what makes them different from electric fields. We know that electrostatic fields always begin or end on charges, so they have a beginning and they have an end, and as a result, the divergence for an electric field is not 0. In fact, it's equal to an expression that involves the charge density that's producing the field. So here, if B lines always form closed loops, then they will never have a divergence. We can also express the same physics in the language that says this means there are no magnetic monopoles. There's no magnetic equivalent to a single positive charge or a single negative charge, such as we find in electrostatics. Anytime you find a magnetic material, it always comes in the form of dipoles, plus and minus poles joined together. Now, what about using Ampere's law? I hinted earlier that Ampere's law might be useful to us in special situations, much as Gauss's law is useful to us in electrostatics when there is a high symmetry charge distribution. So that's also true in magnetostatics. When we have a high symmetry current distribution, Ampere's law is useful to us because it allows us to find the magnetic field often much more easily than we would have found it using the Biot-Savart law. Let's look at a very simple example. We'll pick a high symmetry case that we already know the answer to, just so we can check ourselves. And this is nothing more than the long straight wire carrying a current I. But it's a very simple one, but it does illustrate all of the steps that we need to use in applying Ampere's law to find magnetic fields. So what we want to do is find the magnetic field a perpendicular distance s away from this long straight wire carrying a current I. And the first thing, just as we talked about with Gauss's law, the very first step is to draw the distribution, in this case it's a current distribution, and sketch the field lines. So here's the side view of our long straight wire, and if we look at an end view of it, we can see that it would be it would give magnetic field lines that circulate around it in circular loops. And I've showed that both in the side view and in the end view. And so you should always draw these into your sketch because the symmetry of these field lines will often strongly suggest what type of Amperian loop you will use in order to calculate the line integral that's in Ampere's law. And that's very important. What this suggests, since the field has this circumferential nature, it's always in the phi hat direction around the wire, then it would make sense for us to choose an Amperian loop that is a circle of radius s centered on the wire. Okay, and we'll illustrate this in the next slide. Why is this helpful? Well, it's helpful because if we choose the Amperian loop as the dotted line, then everywhere on that loop, the B vector and then the dl vector will be parallel to each other. And this is because of the nature of the circle. So if, as shown in here, the current is pointing into the page, then the B everywhere will be tangent to the circular loop, as the dl vector is, so B and dl are parallel, which means, starting from Ampere's law in the integral form, then B dot dl, which is B dl times the cosine of theta, will just give us B times dl, because B and D are parallel. Now, that's the first step, simplifying the dot product. And this only worked because we chose a circular Amperian loop in order to evaluate the line integral. You always have to choose that loop yourself. But the first step is drawing the field lines, because usually the loop will have the same kind of shape as the field lines. Now the next step is we're trying to solve for B, and what we notice is because of this cylindrical symmetry, no matter where we are on the loop, the B should have the same magnitude because it will be the same distance away from the wire. So the B can actually come outside this integral and then give us nothing more than the line integral of dl around the loop. And adding up the length of these dl segments all the way around the loop gives us the circumference of the circle. So we get B times 2 pi s equals mu naught I, and of course this recovers the result that we earlier derived using the Biot-Savart law. B is equal to mu naught I over 2 pi s. So just as with Gauss's law, we won't be able to tackle every problem where we might want to find the magnetic field using Ampere's law, but there are many important problems that we can use Ampere's law to attack. And even when we can't completely use it rigorously, it often can give us a reasonable approximation for what the correct field would be. So here, just a summary of the kinds of symmetries of currents for which Ampere's law can be used. We certainly can use it to attack cylindrical current symmetries, much as this long straight wire is. Then there are also planar symmetries. If we have a flat plane that is carrying a surface current, we can use Ampere's law for that. And then there are also some special cases of wires that are wrapped around into certain configurations. And we'll see, you'll see in the book, that Ampere's law can be used to solve the case of an infinite solenoid if we want to find the magnetic field inside the solenoid. And then a solenoid, being a cylindrical frame that carries a current wrapped around it circumferentially, if you wrap a solenoid around into a circular shape, you form what's called a toroid. And the toroid is also a geometry that has the right kind of symmetry for Ampere's law to be applied. So we'll do some examples in class, and that's where I will see you next.